Welcome everyone. So this is our 117th live stream geometry. We have me and 3 other people here with us today, and I am going to do some problems from a couple different contests. So some are from the USAMO, so that's the US Ersatz Math Olympiad, and it's run by Evan Chen. So he has a great channel, so I definitely recommend checking out his channel if you haven't. And then the others, there's one from the Taiwan team selection test, one from an Indian contest, and I'm not sure about the rest. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So I will begin by sharing my screen. So give me just a moment. All right, can you all see it? It says it's loading. Okay, now I think you can see it. So here's the first problem I'm looking at. So this is from the Taiwan team selection test in 2018. So we want to draw the in-center, circumcenter, and centroid of a triangle ABC. So here is the, let's see if you just joined. So this will be the circumcenter, and let's draw the in-center. Let's call it I. All right, hey Anurag, thanks for joining. And G is the centroid. So I haven't made any tool for the centroid. So I'll draw that right now. Okay. And it should be G. So we have this, this, and this. And they intersect at a point, which let me rename this first. It's K, and this should be G. And X, Y, and Z are on the rays B, C, CA, and AB, so that BX equals CY equals AZ. Oh yeah, I could have done that. Yeah, the only thing with that is, yeah, you don't see the medians, but I don't know how important that really is. So compass, I'll use the compass. So we want BX equals CY, and we want that to equal AZ. Okay, so this is Y. And F is the centroid of XYZ. Okay, so now I should probably use that tool. So we have triangle XYZ, and it is triangle center 2, right? So F two. Why did that not work?
Wait, let me check actually. I guess I can be wrong.
Oh, there we go. All right, now it looks like the font is dry. Sorry, I'm going to mute you. I think you're outside, but yeah, if you want to speak again, you can just unmute yourself.
Okay.
All right.
Hello.
Hey, Stefan, thanks for joining. So we're on our first problem, and I'm trying to make, where'd the in circle go? There used to be So this is the centroid. Should I ever draw the incircle? Maybe I just never drew it. Yeah. Okay. I could have sworn I did. So anyways, so this is I. We want to show FG is perpendicular to IO. I wonder if it's a IGFO is a rhombus. No, well, I don't think it's a rhombus. Interesting. Okay. So let's call this, I don't know, B or something. Let me check the chat. Triangle center ABC2. Yeah, so that is G. Okay, so we have a line connecting two centroids. And we want to show it's perpendicular to IO. So this is kind of interesting. Basically, we're saying as X moves, F moves on a fixed line perpendicular to IO. I don't know if we could use like vectors or something, because F is like a third X plus a third Y plus a third Z. And since Bx equals Cy equals AZ, I don't know if it's that easy to do though.
Yeah, I also think vectors are a good idea, because centroids are good with vectors.
Okay. So let's see.
Well, technically, we could complex bash this, since that is kind of the same as doing with vectors.
Okay.
But yeah, we prefer not to bash.
Yeah, complex bash gives a nice way to deal with the centroid.
Okay. So how do we use the condition Bx equals Cy equals AZ?
Can we use Seva in some way?
What?
Using Seva would work, I guess.
Using what?
Seva theorem, he said.
Oh, Cheva's theorem. Okay. We don't know that AX, BY, and CZ concur though, right? We could also try to find the power of F with respect to both circles and show that if we subtract it, it's the same as for G. I don't know how easy that is though.
Maybe we do something like moving points.
Okay.
If we could like show F lies on a line when X moves, that would be useful probably.
So if X equals D, then is Y the touch point of the X circle? I think it is, right?
Not sure.
Actually, I don't think so, because Bx equals Cy, that would mean this is BB, but that's not, yeah, so that's not true, actually. Let me just fix this. So maybe we could work in reverse. Like we could drop a perpendicular from G to IO. And we could show that like if you pick a point on it, then maybe you could construct the triangle XYZ, and then it would have this property. So yeah, like for a certain choice of X, F would be a third X plus Y plus Z. And then
Wait, can we like consider bx x dash to be like a point on AB such that bx is equal to bx dash?
okay, so are you saying, sorry, so like this, so we draw X prime right here?
Yeah. I guess that can help in interpreting the length condition, because
Yeah,
like then you can sync it with this encircle condition as well. Then
yeah, I like that. Yeah, because then X is the touch point for, well, no, it's not the X touch point, but we have like a symmetry. I like that idea. So
Are X, Y, Z, and X prime cyclic?
hold on one sec. Let me draw Z prime and then I'll check that.
Yeah, probably aren't, but worth checking, I think.
All right. X, Y, Z.
Yeah,
What do you think X prime?
yeah, but I think maybe we should add the midpoint of arc BAC.
Okay.
That is because then, because we have that BX prime is YC, then we will have a cyclic quadrilateral.
Oh, I see what you're saying.
Yeah, that's because of spiral similarity.
Yeah.
great, yeah, that's good.
Not sure if it helps though.
But BX is BO plus OX. Yeah, that's not bad. So I wonder, like, because so the vectors BX, CY, and AZ have the same length, right? And F is like a third X plus Y plus Z, whatever center you choose. But like if you move X, all these vectors scale by the same amount. So I wonder if you could use that to prove that the vector FG is just scaling by a certain amount. And so therefore, that's why F stays on the same line. Does that kind of make sense? And then you'd only have to prove it for one special case if that were true. Yeah, I think vectors can easily prove that FG is always in the same direction, because so the vector Bx is like the vector X minus the vector B. So like I think it's just a calculation. So the vector FG, so F is a third X plus Y plus Z, G is a third B plus C plus A. When you subtract the two, I think you get the vectors Bx plus Cy plus Az, and those are always the same length. So if you change X, you're just scaling the vector FG. And so I think we only need to prove it for one case of the point X. Does that make sense?
Could you just repeat one more exactly how you did it?
Yeah. So, sorry. So, oh, Yusuf just joined again. So the vector, sorry, this is like hidden. I didn't mean to do that. The vector FG, it's like you could take an arbitrary point, let's say O, and consider it the center of your coordinate system. But the vector FG, it's like the point G minus the point F.
Yeah, let's say we are doing complex numbers. That is just easier than saying vectors.
Vectors. So G is a third A plus B plus C.
Yeah.
And F is a third X plus Y plus Z. So when you subtract the two, you get a third the vector Bx or plus the vector Cy plus the vector Az.
You get B minus X and C minus Y and A minus Z.
Okay. So I was thinking if we were using vectors, that would be the vector Bx plus the vector Cy plus the vector Az, right?
And those three sum to those three, when you sum those vectors, they always have the same direction.
Exactly.
Why is that so?
Well, because like if you pick one choice of X, they'll have a certain direction. But then if you move X, they're all, each individual of these three vectors is in the same direction, but you're just scaling all of them by a constant from what it was before. So like whatever the direction is for this choice of X, if I moved X here, that would be scaling this segment by a factor of K, but all three of these get scaled by a factor of K. So you're just scaling the whole sum by a factor of K. So the vector would have the same direction just by a factor of K. Does that kind of make sense?
It does, yeah. So yeah, we need to show the problem for one special point X.
Yes. So maybe X equals D.
I think D is a bit strange point to work with.
Yeah.
Maybe it's better to take the midpoint of BC.
Okay.
Yeah, because you kind of get some symmetry.
Yeah.
Oh, and yeah, also since then X lies on AG, this, yeah, I think M is the best option. The midpoint, I don't, it is K, right?
Yeah. I wonder if this is a kite in that case. I don't know for sure, but. Well, no, because IG and O are, well, it could be. But IG doesn't always equal GO, so it's not going to be a kite. One sec, I'll be right back. All right, I'm back. So if X is the midpoint, and CY would be half of BC and AZ would be half of BC. Let me see, I wonder if there's a point X which, I was going to say, I wonder if there's a point X which makes AZXY cyclic, but I don't think so. What happens as X approaches B? So as X approaches B, F approaches G, but we need to show that it's like in a direction perpendicular, which is not that easy.
Wait, how can we interpret this weird length condition actually?
How do I interpret what?
This length condition.
Oh, so are you asking how I know that we can prove it for any point X, then it'll show it for the whole problem? But yeah, we're trying to figure out, yeah, how do we use this length condition? Yeah, I'm not sure.
I have another idea. Maybe we set X equal to C.
Okay. So then, yeah, points Y and B will be, or point Z will be somewhere on the extension of AB, right?
Yeah, yeah. But look, when you take point, just let me see. No, I thought of something. Never mind. But yeah, maybe it is useful.
Okay.
It's like that. I mean, we can try.
All right. So let's see. So So yeah, I'll hide segment AB and then I'll redefine Z to be the point on that ray. But then actually let me use the algebra. Maybe that'll make it easier to redefine it. So Z is the intersection of, let's see, this is ray A, so maybe this will work. Maybe, let's see. So A, that ray, this would be awesome if it just worked like that. It didn't work. I wonder why. Oh, because it's calling this the ray between A and Z. We want this to be the ray from A to B, and then Z, maybe that'll work. So if I then, why didn't that work? So intersect P with, let's do P with A. There we go. I think that does it. All right. So let me hide some things. I'm going to hide the circle for now. Okay. What is it? I'm going to hide this one too. Okay, I think. So if we let X equal C, let me make this triangle so that AC is longer than BC. That might help. So then if X equals C, I shrink it. We show the problem in this case. So then we want to show FG is perpendicular to IO. So CY equals BC, so that gives an isosceles triangle there, and AZ equals BC. So yeah, Y and Y prime are, so yeah, Y prime equals B basically. This reminds me a lot of another problem I did on my channel about the line IO, but I don't think it was like BX equals CY equals AZ. I think it was like there was like a point on AB and a point on AC, and it was like BX equals CY, but it wasn't like in a circle. They were both like on the same side.
I think I know what you're talking about.
Yeah.
If you took a line on point on AB such that the segment B, that point is equal to BC, I don't know, call it like P or something, then PY should actually be perpendicular to OI.
Using that problem on my channel?
Yeah.
Okay.
I think I heard of that fact independently from
my
yeah. I mean, it may be the case that I first discovered it there on your channel, but it is not the only source I saw that.
Okay, so did you say TF is perpendicular to OI or
TY.
TY is perpendicular to OI? Okay. So let's check that. TY. Okay. And maybe FG is parallel to, well, it would have to be, yeah, if the problem were true. So interesting. So in this case, what would vector FG be? So so we still have BX, CY, and AZ. So it would be third of the sum. So T is the point such that BC equals BT, and T. So we could almost call it C prime kind of. So BTC is isosceles. So we want to show TY is parallel to FG. Maybe we could use some kind of homothety. So like a homothety about G takes ABC to KHJ. Maybe we could see where it takes T and Y to. Going to take T to some point on KM or KH. And it's going to take Y to some point.
Wait, can you take the homothetic center of the circumcircle of ABC and XYZ?
Draw the homothetic center of those two. So ABC and XYZ.
But those triangles are not homothetic.
Yeah, the triangles are.
Yeah, you are right.
But it does seem okay. So BT equals BC and CY equals BC. And we want to show them that TY is parallel to FG. I wonder if that's just a vector calculation, because So we can, so T so F would be a third x plus y plus z. And yeah, I wonder if that reduces to a vector calculation. Let me write it in my notebook. But yeah, we just want to show Ty is parallel to FG, right? It's a third of x plus y plus z, which is a third of x equals c. And then y so y I could leave at y, and then z is AZ equals BC and BT equals BC. So it would be like we could define T in terms of Z. So T is basically the vector AB plus the negative of BZ. So we could define Z in terms of T. So I think I might have this. So then F minus G is a third. I think it would reduce to T minus TA minus A. Minus A. I think this vector might actually just be some 2A minus B. But like, I wonder if this is actually 3 times this length. Does it look like it? Let me check if that's actually true. Or it's like always. Yeah, so I think if my calculations are correct, it's might be that Ty is 3GF. 6.47. So 18. Yeah, I think it is. So yeah, Ty is going to just be 3FG, and it's just a vector calculation, which isn't the most elegant, but
Can we go to another problem?
What?
Can we go to another problem?
Do you want to go to another problem?
Yeah. So I solved this one, but with complex numbers.
Okay. Let me type up the solution and then we'll move on to another one.
Yeah.
So, okay. So first we try to reduce it to where x equals c. I don't even know if we really need that. Well, I mean, it makes it easier though. Yeah, I use that because that's where I use that previous problem on my channel. So, okay, so the vector fg I don't know how to do vectors notation. Is it like, so we have, so fg is it's going to be f minus g, which is a third of x plus y plus z. Actually, gf is probably easier. So that's g minus f, which is a third a plus b plus c minus x minus y minus c. And so x so yeah, so oh yeah, I should split this into two. So yeah, I'm gonna try to type this up as fast as I can. But what happened there? Okay. So GF, that's going to be G minus F, which is a third of A plus B plus C minus X minus Y minus Z. And that is a third of B minus X, B minus X plus C minus Y plus A minus C, which is a third of bx plus ay plus cz. And then since bx, ay, and cz have the same length, okay. Since bx, ay, and cz have the same length, this quantity will just scale as we move x, but maintain the same direction. So thus we only need to prove the problem for a special case of x. All right. So let x equal c. Then from a previous video, ty is perpendicular to IO. TY is perpendicular to IO. And then we could show just by vectors that TY is a third FG. Right. So yeah, they're all equal, but yeah, they have different direction. Yeah, I don't know, but yeah, so these three are equal, but with a different direction. But if you just move X along BC, then all three of them are scaling by the same factor. So the direction is going to be the same and the length is just going to scale. Then here we would have.
Yeah, you made some typo here. That's what he's talking about. I think it should be BX, CY, and AZ.
Oh, good point. Yeah, it should be. So yeah, thanks for catching that. And then the rest is really just the length chase. So we have then we have GF is equal to a third. So we still have that same expression. So we would have A plus B plus C minus X minus Y minus C. And that would be equal to a third of, so A plus B plus C is going to be the same, but X is actually point C, and then Y, so Y, I think I'll just leave as Y, but then Z, we can calculate that because basically Z and T are symmetric. So I think Z is going to be basically vector AB plus BZ. So vector AB plus BZ, and AB plus BZ is AB minus AB minus AT. So yeah, I need to fix that, but sorry. I'll just write it right here. So AB minus AT. So the C's cancel. And then AB is like B minus A. And then vector BT is vector BC. So once you calculate it, you should just get like this should simplify to a third of T minus Y. I'm just going to write that and be lazy. So we use that. So yeah, do you guys want me to finish the calculation or just say this simplifies to a third T minus Y?
Simplifies, of course.
Okay. So TY is parallel to FG. And that means that FG is perpendicular to IO. All right, let's move on to the next one. So yeah, this is just a lot of vectors. So Yusuf sent me this problem. This is from the USAMO. So we have a cyclic quadrilateral where the opposite sides are not parallel. And then PQRS are in the interiors of the segments. And we have that condition. So let's think about that. P is on AB. So PDA equals PCB. So how do we, that basically means, yeah, what's the best way to try to find that point P? PDA equals PBC, and we want it to be on this segment. So this is P. Yeah. How would we figure that out? So basically, if we extended these points to meet the circle, then the resulting line would be if you connect them, would be parallel to AB. Oh, it hasn't happened yet. Okay. Then we better not do this if it hasn't happened yet. Sorry, I thought you were. Now I'm almost worried about making.
No, like it can be
No,
an
that's
old
probably just
problem
a
of
mistake.
USAMO.
Oh,
Yeah,
what?
that's just a typo, I guess. USAMO.
Oh, maybe because yeah, I thought the solutions had been put on the internet already.
I mean, like USAMO 2023 hasn't happened yet, but it can be an old problem of USAMO.
Okay, but so let me just make
I
100%
think it's
sure.
from 2022 actually.
2020.
Yeah, it's from 2023.
Okay. So are you sure it's 2022?
I'll check right now.
Okay.
Yeah, let's make sure so that I don't get in trouble.
I'll check right now.
Okay. Yeah, I don't think it would be on here yet.
Yeah, this year. Yes.
2022 or 2023?
2022. Yeah, this year because it's the fourth USAMO.
Okay. So let me see. So there we go. Okay, so it's the fourth one. Okay, so if he has a solution here, it has to be already finished. Okay, so we can do it. So what does it mean? How do we find the point P that has that condition? How do we find the point P where angle PDA is PCB?
I guess they are trying to imitate some tangency condition.
Oh, so maybe use tangencies?
Yes.
Okay.
I mean, exactly, it's not correct, but I guess intuitively.
So if those angles were equal, then if we drew this circle and this circle, it would basically mean the tangent at A to this circle and the tangent at B to this circle would make an isosceles triangle. So let's think about that.
Oh, I think I know. I haven't proven it, but looks like it's true. If you intersect AB and CD.
AB and CD.
AB and CD, yes.
Okay.
then FP squared is FC times FD.
FC times FD.
Yeah.
Okay. So
Basically, yeah, PCD is tangent to AB, I
okay.
think.
Wait, that resembles an old ISL geometry, I guess. But in that, AD and BC were parallel. Like,
Mm,
So that squared equals that times that.
so you say that is not true, or
what?
I mean, I didn't understand what you said before.
Actually, like I was saying that it kind of resembles an old ISL problem.
Oh, okay.
Okay, so we should let's see. This squared equals this times this. So that means that if we drew the circumcircle of PCD, then this would be tangent. So we want to draw a circle through C and D that's tangent to AB. So it's going to have a center on this perpendicular bisector. And we want it to be tangent. So yeah, how do we do that? That shouldn't be that hard, right? Circle tangent to AB.
Yeah, you can do it with power of a point. If you draw in the tangents from E to the circle, then you could get the length EP.
Oh, yeah, that's a good point. That's a lot easier. Okay, so.
And I think that circle and the other one for the other intersection should be useful here in this problem, just because of it is kind of, yeah, the problem is made up of them.
So yeah, I'll leave those points in. And so that should be point P.
And also, yeah, you can easily angle chase that point is actually the point P.
Okay. Okay, so we come up with point P that way. And then for the point on CD, would this be, I guess, similarly, that would be R, probably. R is
yeah,
CD.
it should be.
Okay, so that's R. Let me just make this look better. Okay. And then as far as Q and S, let's think about that. Would I instead of letting AB meet CD, would I want to draw the BC meet AD, right? I'd want to draw that.
Yeah.
And I draw the tangents. I guess there would be one more step, which is showing that the point P is unique. Like there's not another point that satisfies that. But I'm guessing that's probably not that hard. So let's try to make HI a little farther above B and C. So if I move B a little bit down there, I think that looks better. Now G and P are kind of close, but let's see. Yeah, I think it looks okay. So basically then we would have these 2 points. So this would be Q. And this would be S. And we want to show, so let AQ meet BS at X. And I'm guessing DQ meets CS at Y. And we want to show PR and XY are either parallel or coincide.
I mean, in either way, if you prove that they are parallel, you are done.
If we can show they're parallel, then what? So yeah, PR is like a chord of this circle.
Yeah, we don't really need PR in this problem. That is because we already showed that P and R lie on this circle.
Yeah.
So line PR is just the line perpendicular to the bisector of angle AED.
Yeah, so we just need to show
That XY is
XY
perpendicular to the angle bisector. Yeah.
Yeah.
And also another idea, I think, which is useful, it should be useful, is that we can use Pappus's theorem
Okay.
to show that XY goes through the intersection of diagonals.
Okay, so by Pappus's theorem, I guess we might as well call it Z, and then X, Y, and Z are linear.
Yeah.
And we want to, so yeah, we could kind of work backwards. So we could first define point Z, and then we could take a perpendicular to the angle bisector of AEB. And then we want to show it passes through X. And then by the same argument, we can show it passes through Y. I wonder if there's anything special about that point. So this point right here, we can call it K. Are KB and KC, maybe EBKC is cyclic. Let's check that that's actually true. Yeah, it looks like EBZKC is cyclic. So if we could show that, that would help.
What is K?
K is like the perpendicular from E. Well, I guess there's a couple ways.
It is the angle bisector thing, right?
Yeah, K.
Yeah, but it is not true. It can't be true that those are cyclic. Then we must have that AD is the diameter.
E or EZ would be the diameter, right?
Yeah, EZ is the diameter, but also because then we would have that ABD and ACD are 90 degrees.
ABD and oh, okay. So it's just because of how I drew this that it looks true. Yeah, you're right. It's not actually true.
Yeah.
Okay. So yeah, I should probably draw EF and EG. So yeah, these are tangents. Are F, Z, and G collinear? That's Picard's theorem, right? Yeah, I think so. Yeah, because F, Z, G, and H should be collinear. Okay. By Picard's theorem. It looks so close to line XY, but oh well.
So it looks like the line XY is the bisector of angle BZA.
BZA?
Yeah,
Interesting.
it is probably obvious if the problem were true. So I think we could do something like trig Trevor
Okay.
on triangle BZA. If we did trig Trevor, then we would, let's say that ZX is like the bisector.
Mhm.
Then those two signs are trivial, they're just equal. And then we would have to find the sign ABS over sign SBD.
Mhm.
And that looks pretty good to be calculated.
Because we have the angle equality, so angle SBA would be SCB. So we'd have like sine of SPB over sine SCB.
I didn't really think of that. You could just kind of find AS or SD. And with that, you can find the ratio of signs.
Okay.
But yeah, maybe you can also do it directly from the problem condition.
Can you please move the figure a little bit?
You want me to move the figure a little bit?
Yeah, I want to check something.
Okay.
QXYS looks like a kite.
XYS. You think it might be isosceles?
No,
Oh,
I think it's a kite.
So yeah, QXYS. It does almost look like a kite. Let's see. So, so that would mean QS and EK would be parallel.
Equal. And QX and QY implies it's equal.
QX and QY are what?
No, nothing.
So I wonder if EQ and S are collinear. No, that's not true.
No.
But yeah, it does look like this is probably a kite.
Well, I think we can easily solve the problem if we prove that it is a kite.
Oh, really?
Because we can angle trace, I assume that QS is parallel to the angle bisector of AED.
Yeah, it seems like that should be able to be proven.
Yeah. So, and yeah, it looks like QXSY is a kite. So if we could show that would solve the problem.
So, it's a kite. So we have angle XSQ is equal to angle it's equal to angle H. No, XSQ. So angle XSQ is equal to angle HSQ minus HSB.
Mhm. Yes.
So let me draw this one.
Yeah.
So, and it's equal to SQ SQ.
Oh, it might just be an angle chase. Yeah, from what you're saying. Because HSQ we can calculate in terms of, because HSQ is isosceles, so we can just calculate that in terms of angle CHD. And then HSB. So
HSQ minus HSB minus HSB is equal to angle SQH
mhm.
minus angle SBC. No, sorry, no.
It looks good, actually, to me. So HSQ, okay, angle BSQ is HSQ minus HSB, and HSQ is equal to HQS because we have that circle.
Yeah, HQ minus.
And yeah, HSB
Okay,
is BCS because BSC is tangent to AD.
yeah. So
And
it implies, and it's SQH is minus SCB is equal to a QSC.
So that shows it's the angle bisector. And
Yeah, which implies that's a kite.
so once we know it's the angle bisector,
Yeah.
so we'd have it both ways. So QS bisects this angle and SQ bisects that angle, which means it's a kite.
Yeah.
Okay. And then
so that proves that XY is perpendicular to QS,
mhm.
and that solves the problem after another angle chase.
Okay, so it's just an angle chase to show that, yeah, it must be an angle chase to show that SQ is parallel to the angle bisector of AE.
Yeah.
Because it's perpendicular to the angle bisector of QHS. So basically we just need to show the angle bisectors of CHD and AED are perpendicular, and that's just the angle chase.
Yeah. So we can skip the angle chasing.
Yeah, we can skip the angle chase, I agree.
Yeah.
Right. I like it. So I'm gonna delete point K. Yeah, this is a good one. Okay, so I'll just say label the points as shown. Did we use point Z? I don't think so, right?
I think we didn't.
All right. Yeah, I think it's clear from so label the points as shown, and then it's easy to show that by an angle chase that PQRS are as defined. I'm skipping a lot there, but it's okay. It's easy to show that PQRS match or correspond to the original definition by an angle chase. Okay, and then so now we're going to do the angle chase showing that this is a kite. So we let me just write it on my paper and then I'll type it up. So we have angle QSX is angle QSH minus, yeah, I think I should write out something for that. So that's QSH minus BSH, which is HQS minus, so BSH is HQS. No, sorry, BSH. So HQS. What was BSH again? I forgot. Is that BC or BCS? I think so. Yeah. And then, which is QSC. Okay, so I'm just gonna, that's the only angle chase that I'll actually type up. So angle QSX or B is and then similarly angle SQA equals angle SQV. So then we have a kite. So that that means that QXYS is a kite. So that means that for QXSY implies so XY is perpendicular to QS. And then by an easy angle chase, QS is, so QS is perpendicular, I'll just say by an easy angle chase. QS is parallel to the bisector of AEB. Implies so which is perpendicular to PR. And that PR is parallel to XY. Right, so that solves the problem. So I will move on. So let's see, what time is it? So a little less than halfway through. So here's another problem from the USAMO. So this is like a conditional problem. So we have a cyclic quadrilateral, and then we have a circle centered at O. Passing through B and B. Well, all right, so looks like that Feng is joining. So I guess O doesn't have to be this O. It could be some other O. So this would be like a point O. And so AD doesn't have to be a diameter. So, okay, so we have a circle. Hey, Fun, thanks for joining. So that's through B and B, and it meets BA at E and BC at F. And then we have the orthocenter of DEF. So I'm going to use, actually have a tool for this. But I just need to rename stuff. So this would be H. So let me rename this point. Okay. And this will be H. And prove that if lines AC, DO, and EF are concurrent. So when would that happen? Let's see. So we want AC, DO, and EF to be concurrent. So like that. So I'll make it bigger. So like this. So if they concur, then ABC and EHF are similar. That's kind of an unusual statement.
The first time I see a problem that asks for similar triangles.
That has what?
Like ask for similar triangles.
Oh yeah. Yeah, I haven't done too many on my channel like that. Okay. So O lies on the perpendicular bisector BD. I wonder if these circles are the same size, if these concur. Guess we could check that. Although I'm not sure if that's actually true. So if I reflected this circle about BD, no, I don't think they're the same size. No, they can't be, because one has radius OB and the other has radius BP. So if ABC and EHF are similar, then that would mean the circumcircles of EBF and EHF would have the same size.
I think there is some isogonal line lemma in this problem.
Oh, really?
Yeah, it looks like that angles, actually that DE and DC are isogonal in angle ADF. So DE and DC.
DE and DC are isogonal in ADF.
Yeah,
Interesting.
maybe that can be angle traced. But yeah, we could use then isogonal line lemma to see that. Let me see if you have that point. EF intersection AC, yeah, then DJ and DB should be isogonal in angle ADF also.
DJ and DB.
Yeah,
Okay.
that's by isogonal line lemma.
Yeah.
But DJ is DO, so maybe we would get some angle condition.
Yeah, that looks pretty good. So basically this angle would equal this angle. And it's not exact because, yeah, I didn't draw the figure exact, but it does look good. So I think it can be angle chase that angle ABC equals EHF. I think that's an easy angle chase. So we just need one more of those angles to be equal.
Which one should be equal to which one? Maybe EFH is BCA, right?
EHF and ABC, it's easy to prove those are equal.
Yeah, I know for that, but we should prove that EFH is BCA.
Yes.
Yeah, okay.
I think it's equivalent to saying that FDJ is equal to, what do you think about this? FDJ is BEF? Maybe. Wait. BCA. Yeah, I think it might just be an angle chase. So we want to show that BCA. We want to show that this angle equals this angle, but this angle equals this angle, and then use the isogonal line lemma. Yeah, I really think it's just the isogonal line lemma, to be honest. Yeah. So yeah, it's really just isogonal line lemma and an angle chase. So yeah, it's not the most complicated problem. Okay, so I'm going to type it up. Suppose A, B, D, O, and EF concur at J. Then by the isogonal line lemma, okay, so first of all, I'm going to show that EHF is ABC. So EHF is 180 minus EBF. Which is EBF, which is ABC. So that's the first angle. And then the other one, how did we do this? I'm trying to remember. So DH and DO we know are isogonal. Oh wait, or not necessarily. Okay, so DE and DC we showed were isogonal by an angle chase, right? So let me do that angle chase.
Yeah, it is really easy. You just have that angle ADC is 180 minus ABC, which is EDF.
Which is EDF. Okay, so angle ADC is 180 minus ABC, which is 180 minus EDF, which is EDF. So ABC is 180 minus angle ABC, which is 180 minus angle EBF. Which is angle EBF. So that means that DE and DC are isogonal in ADF. And then by the isogonal line lemma, that means that DJ and DB are isogonal in ADF. And then from there, it's just an angle chase again. So let me write it out on my paper, and then I'll type it up, and then we can move on to the next problem. So we have angle BCA is angle BDA, which is angle FOJ, which is angle ECH, which is angle EFH. And that solves it. Okay. So and that means that ABC is similar to EFH. So yeah, it's not a difficult problem. All right, let's move on